Okay, let's start the session for track one. So, hello everyone, I'm Seokhwan Kim from Amazon Alexa AI. Today I'm going to share with you the overview of our track Beyond Domain APIs, Task-Oriented Conversational Modeling with Unstructured Knowledge Access. The main motivation of this challenge track came from this scenario. So I think most of you are familiar with this kind of conventional task-oriented scenarios, like asking some train schedule with some constraint. And using this kind of, for this kind of request, usually the system is supposed to understand the user's intention, and based on the understanding result, the system tries to access to the domain API or databases to find information or to take some action. And then the system can provide information in the next turn, next system turn. But the question here we had was like this. What if this user asks a question like this? I also need to bring my dog. Do they allow pass? So this is a kind of the PEP policy related question for the train. But the problem is that this kind of information is out of the scope from the domain API or database. So what the system can do is just to say like this, sorry, I don't know about that. But we already know that this kind of information is available somewhere on the web. For instance, the trainer page usually have some FAQ or documentation about this kind of policy. So what we can do in this case is to find this information by ourselves while we were doing the interaction with the system. But this is not very convenient and efficient. So the goal of this challenge track is to move this information seeking process from the user side to the system side instead, so that the system can directly answer the question based on the result from the search from external knowledge sources. So for tackling this kind of problem, so we proposed this baseline architecture, so which decouples between the existing task-oriented conversational models and the another additional pipeline to handle the external knowledge to answer the question or to provide the corresponding information to the user. And our challenge track focus on this second branch only, including the three subtasks: knowledge seeking turn detection, knowledge selection, followed by knowledge grounded generation. So here, I'm gonna walk through one by one. The first subtask we had is knowledge seeking turn detection, which was formulated as a binary classification task, which takes the user turns and dialogue history as the minimal input, and also the knowledge path and API and database info as the optional inputs. And the goal of this task is to decide, to predict the binary classes, whether a given turn can be handled by the API or it requires any external knowledge. For example, in our previous example, the first user turn is obviously can be handled by the API. So it should be predicted as the API-based turn for this knowledge seeking turn detection task. But on the other hand, the second turn is out of the scope from the API. So the expected result from this knowledge seeking turn detection component is the knowledge seeking turn for this case. And once we get this kind of knowledge seeking turn predicted by the first knowledge seeking turn detection component, we move forward for the knowledge selection to actually find the relevant knowledge from our knowledge base. So we formulate this knowledge selection task as a point-wise ranking task. And the input to this component is similar to the previous knowledge seeking turn detection task. So it includes the knowledge seeking user turns, dialogue history. And here we add an additional input, the knowledge candidate itself. And here we feed every candidate from the knowledge base into the input. And the expected output from this task is the relevance score or the binary class, whether a given turn and the knowledge candidate is relevant or not. So for our previous example about the pet policy on the train, we can consider some negative and positive examples for the knowledge selection. For instance, the first one is the train policy, but this is not for the pet policy, but for the future policy. So this is irrelevant to the request from the user in this example. And the second example knowledge snippet we have here is about the pet policy, but this is not for the train, but for a hotel. So this is another negative example. And the final one is the correct one that the system is supposed to select from all these candidates. So after getting the relevant knowledge candidate from the knowledge snippet from the knowledge candidate, we go for the final task for the knowledge grounded response generation task. And this is typical dialogue generation task, but here we incorporate not only the dialogue context and current user term, but also the selected knowledge from the previous task. So the input include the knowledge seeking user utterance, dialogue history, and selected knowledge snippet from the second knowledge selection task. And it aims to generate the system response, which is naturally connected to the previous dialogue context and also accurately grounded on the ground truth knowledge. So for this dialogue context and the selected knowledge, we expect from the system to generate this kind of the system response. Right, and to study all these subtasks in the pipeline architecture, we collected the data. And our training and validation data set was originally from the multiverse data. And as you know, multiverse data is the multi-domain, the task-oriented conversational data set. But this original data doesn't include any out of the API coverage terms. So it is only for the API-based terms. So what we did on top of this multiverse data was to augment the conversations with some additional out of API coverage terms grounded on the external knowledge sources, particularly for the FIQ formats. And this data augmentation was done by digit 3, the sequence of the crowdsourcing tasks. The first one, in the first task, we asked the talkers to select a position in a given conversation to insert a new additional term discussing about a given subject. And then and in that selected position, we asked the talkers to write down the actual question about the subject. And in the final AMT task, we collected the agent responses to answer the question based on the ground truth knowledge we provided to the talkers. And here are the statistics of our data set for the training and validation data set we released in the beginning of the challenge. So we had roughly 80,000 total instances, and about 21K of them are the newly augmented terms, which means that 21K of the out of the scope, out of the API scope terms. So based on the external knowledge. And the right-hand side, you can see the statistics of the knowledge snippets, the FAQ knowledge in terms of the number of entities and number of FAQ pairs. And using the collected data, we developed the baseline models for participants to start with. For the first knowledge seeking term detection task, we developed the neural utterance classifier, which is basically a supervised binary classifier which takes a dialogue context only. And we trained this model by fine-tuning GPT-2 with binary cross entropy loss. So you can see a brief, the overview of the system architecture on the right-hand side. And for the second knowledge selection task, we also developed the supervised binary classifier, but differently from the previous task, here the model takes not only the dialogue context, but also each knowledge snippet as well. So we concatenated both knowledge snippet and dialog context into a single sequence, and we feed this sequence to the GPT-2 model to predict the relevance between this given pair. So we use the binary cross entropy velocity, and for training this model, we randomly selected 5 negative examples from the whole knowledge base for the negative sampling. And finally, for this response generation, we also use the GPT-2 using the standard language model objective to generate the responses for given dialog context and knowledge snippet. So here you can see that in our model for training, we use the concatenated sequence of knowledge snippet, dialog context, and ground truth response to fine-tune the GPT-2 model. So in the beginning of DSTC9 track, in the beginning of the challenge period, we released all these data set, knowledge base, and the baseline models to the participant. That was on June 15, 2020. And then our participating teams have been working on their systems for about 3 months. And on September 21st, we released the test data set. And we did both the objective and human evaluation following this timeline. For the test data set, in addition to the remaining part of the augmented multiverse beyond the training and validation set, we added a new data set for San Francisco content, including hotel, restaurant, and attraction. So it includes some unseen knowledge and unseen domain and unseen locale. So this is a kind of the unseen test data set to see the generalizability of each system from the seen data, seen knowledge in the multiverse to this new data set. And here we didn't have any seed data, the base data conversations like original multiverse. So we collected all these conversations, including API-based and external knowledge-based interactions from scratch by ourselves. And it was done by the mechanical Turk experiment for the written conversation. And we also collected some spoken conversations by hiring some people and asked them to do the live conversation. And we recorded the conversations and transcribed and annotated to have the spoken subset of our test data set. Okay, and this is the final statistics of the whole data set we used for this challenge track. And for the automated evaluation, we used this set of evaluation metrics for each task. For the knowledge-seeking turn detection task, we used the precision, recall, and F measure of the detection result. And knowledge selection, we used the recall at K and mean reciprocal length at K. And for the response generation, we use the standard, the typical energy metrics based on the references, including Blue, Mihail, and RADGE scores. And here, one problem we had was that we have the all these 3 subtasks were done on the pipeline architecture. It means that the later in the pipeline, like task 2 or task 3 have some dependencies to the result from the task 1. So here, the thing is that we asked the participating team to generate the task 2 and task 3 result only for the positive instances based on the detection result from task 1. So it means that the number of the task 2 and task 3 results varies depending on the system and the teams, depending on the performances of the knowledge-seeking turn detection component. So just taking the average across all the available turns, available instances doesn't make sense that much to have some fair comparison between different systems. So we proposed some weighted scores for the task 2 and task 3, so which is basically based on the precision and recall of the task 1 performances. So here is the more detailed equation. And you can see that this F1 is the ground truth for the first knowledge-seeking term detection in binary values, 0 or 1. And similarly, we have the prediction result also in binary format. And this S is the target score, and we calculated the weighted score using these additional terms to consider the precision of the test score result. And similarly, we got the recall weighted score. So this is similar to the first equation, but we replaced the denominator of this equation from the sum of the prediction results with the sum of the ground truth labels. And then finally, we take the harmonic means of these two scores, just like F1, and we used the weighted score for every metric in task 2 and task 3. Okay, so after this track, we have received over 100 entries submitted from 24 teams in total. And this was the second most successful challenge track in terms of the number of participating teams from the whole DSTC history. So it was exciting. And this is the word cloud from the system descriptions submitted by the teams when they submit their system outputs. And here we can see some overall trend of our system entries submitted. So so as expected, considering the characteristics of our task, the entity was considered as one of the most important thing to focus on. And we see that the most frequent, the keyword in this word cloud is the pre-trained language models like GPT-2, Roberta, Albert, BERT, BART, or something like that. And it seems that many teams fine-tuned these pre-trained models. And the final keyword, which is notable, is the ensemble. And as I'll discuss some more details about that later, but especially the top ranked teams were heavily used, heavily applied the model ensemble. So based on the multiple different models. So these are the system descriptions. And here, this histogram shows the evaluation result for the first task, knowledge seeking term detection in F measure. And you can see our baseline performance here. And we see that roughly 2/3 of our participating teams achieved higher performances, higher knowledge-seeking term detection performances than our baseline. And especially team 3 and team 19, the top two teams in this knowledge-seeking term detection result. So they achieved around 99%, which is almost a perfect, the F measure. So they did a great job for the knowledge-seeking term detection. And this is the knowledge selection result. And here, our participating teams did even better job than the previous test compared to our baseline. So most of the teams outperformed our baseline in terms of the knowledge selection performance in recall at 1, and especially the best team, team 19, so achieved more than 30% higher recall at 1 performance than our baseline. So this was huge. And this is the final knowledge grounded response generation result. And here, our baseline is located here. And most teams also achieved the higher scores, higher generation scores than our baseline. And team 3, team 18, team 19 were among the best teams that we had in this automated evaluation for the response generation. But so similar to most other energy tasks, these automated metrics are not reliable enough. So this is not perfect. So to have more realistic evaluation result. So we did some additional human evaluation, and it was based on the finalists selected from our the submitted systems from our participating teams, and that was based on the automated evaluation result. And this ranking was based on the overall score calculated by the mean reciprocal rank over all the automated metrics. So the main motivation of this overall score is to give the higher weight for the top ranked systems for each metric. And based on this overall score, we selected 12 out of 24 teams, so which is the top half teams selected for the human evaluation. And we took the best system for each of the top half teams as the finalist. So it means that we had 12 systems to be compared in our human evaluation. And most specifically, we had 2 AMT tasks for 2 different metrics. The first one is the accuracy, to see how much every system output is accurately grounded on the ground truth knowledge. And the appropriateness is to check the naturalness against the dialogue context. And for both tasks, we asked the talkers to assign the score of each system response on a scale of 1 to 5. And we asked 3 talkers to score each of up to 14 responses. So the reason why we had 14 responses is that we had up to 12 finalists from our top half teams, and we also added the baseline and ground truth human responses just for comparison purposes. So we compared the up to 14 responses for each instance. And this is the human evaluation result for accuracy and appropriateness scores. And you can see that as we expected, so all our 12 finalists got the scores between the scores for the human ground truth and our baseline result. And so we took this human evaluation result as our official track result. So as you can see here, team 19 was the best team for both accuracy and appropriateness score. So team 19 was the final winner of DSTC9 track 1. And going into more detail, yeah, this is the correlations between our automated and human evaluation metrics. So as I mentioned before, team 19 was the winner for the knowledge selection performances in automated metrics, and they won the human evaluation result. So we wanted to check whether the success in the knowledge selection affect to the end-to-end human evaluation result or not. So we calculated the Spearman's role between every pair of the metrics in terms of the ranked list. And we observed that the knowledge selection automated metrics have much higher correlations to the final human evaluation metrics. So it shows that the knowledge selection is the most important the tasks to get the higher human performances, human evaluation result. Okay, and comparing our top 2 teams, so this table shows the summary of these 2 teams, and both teams use the pre-trained models like Roberta, UniLM, GPT-2, and Plato-2, and both systems use the model ensemble. So except the generation by team 19. And team 3 added some entity tracking for knowledge selection and data augmentation for task 1 and 2. And team 19 applied the schema guided idea for the knowledge skin detection. And they proposed some improved negative sampling mechanism for knowledge selection. And we can learn more details from the authors later in this oral session for this track. And to get some more evidence about the differences between the 2 teams, So we did some additional human evaluation, so which is similar to our previous human evaluation task. But instead of asking the talkers to assign the scores, we provided two responses from these two systems for the same instance. And we asked the talkers to find a more appropriate and more accurate response between these two. And this is the result from this pairwise human evaluation. And for the appropriateness, both teams got comparable score, more or less the same score to each other, but team 19 was slightly better than team 3. But for the accuracy, team 19 achieved much higher scores, but much more talkers preferred the system outputs from team 19 than the team 3. And I think this came from the better knowledge selection outcomes. And the last thing we have checked from our human evaluation result was the scores depending on the sources. Because in our test data set, we had 3 different subsets, one from multiverse, another from the written conversation about our new San Francisco data, and the other one is the spoken conversation for the San Francisco. And for the baseline, as we expected, our baseline models did a better job for the multiverse, for the scene data, while the performances, the scores for the written and spoken conversation for the unseen domain, unseen San Francisco content, we got some lower scores for this new data set. But when we looked at our top systems, surprisingly, they got even higher scores for the new data set for the San Francisco. So it means that this higher generalizability to the unseen data was the key to success, key to win the challenges, our challenge track compared to our baseline and other competitors. Okay, so here are 3 key takeaways we learned from this challenge result. The first one is that knowledge selection was the most important subtask to improve the end-to-end performances evaluated by the human evaluation scores. And the second one is that ensemble helped to boost the scores, as we saw from our top team systems. And the final thing is that the other key is how to generalize the models to the unseen knowledge. Right, so that's it for the overview, and you can find all the data set baselines and the results, including the actually submitted entries from our participating teams, and also the human evaluation result from this track repository. And also you can find some more details from our track overview paper as well. Okay, that's it for today. So I will be happy to answer any questions, any. So any question?
Can I?
Sure.
Okay, so I'd like to know about the sensitivity of the scores. So you have human judgment and you have a metrics, and when we see the numbers, how to, which number is significant, we can say that 0.2% difference means that definitely, the performance is better than the other systems. Like so I want to know about the exact number to say.
So I don't remember the exact number, but we have the significant test for the human evaluation result. And for the human evaluation, team 19 was the best team. And then we calculate the significant scores. So their result was significantly better in appropriateness than the second best team. But the difference is the accuracy between their result and the second best team was not statistically significant.
So when we compare the speech recognition system, we always set a deduction ratio. If we have the 40% of the deduction ratio, means that significantly we get the gain. Like if we talk about the, the dialogue performance accuracy or knowledge granted, we did want to know about the maybe the number itself, absolute number, doesn't have the meanings, 2% difference in from 80 to 85 or 20 to 25, that meaning is different. So yeah, that should be normalized by the human judgment, and you already have the numbers both sides, and you can make the meaningful numbers to normalize by human scores, and we can say that if 80% accuracy, more than 80% accuracy, this derivative numbers will tell us that
that's a good point. So we haven't done that yet, but so we can try.
You can get it. Okay. Okay, thank you.
So any other question or comment? So we are a little bit behind the time. So I think it's already 5 minutes over. So I think we can move forward to the first oral paper, because I think that may be much more interesting, and there may be more things to learn from our actual challenge participants. So
I have a quick question from someone.
Yeah, go ahead.
Someone was raising hand. I think Karen, did you have a?
Sorry.
Yes, I shouldn't raise hand because probably can't see me. I think my question is, like, do you guys have a study between the correlation of automatic metrics and the human evaluation?
Yeah, so I have presented that in both my talk and the paper, so you can find the details from there.
Okay, cool.
Okay, yeah, let's move forward for the first paper, oral paper in this session. The first paper is from Team 19, so who was the winner of the official winner of our challenge track. The title of this paper is Toward Generalized Models for Beyond Domain API Task-Oriented Dialogue. And it seems that Haitao is here today, right?
Yeah, I'm here. But we are not Team 19, we are Team 3.
Oh, you are Team 3? Okay.
Yeah.
Oh, sorry. Okay. Yeah, so Team 3, the second best team, and this team was the winner in the automated evaluation.
Okay, let me share my screen. Can you see it?
Yep.
Okay, great. Okay, let's start. So, hello everyone, I'm Haitao from Ant Group. I will give an introduction about our work for the track 1. The title of this work is Towards Generalized Models for Beyond Domain API, Task-Oriented Dialogue. This is a joint work with our colleagues at Ant Group and Alibaba. So before that, let's have a quick review of all the tasks, and I will highlight some components of our approach. Take this dialogue, for example. The system here can answer the first question by searching the domain API and domain DB. But for the second question, in the second turn, it's out of domain API. So the system has to search or retrieve some knowledge from the knowledge base and return a table of entity question and answer. With this knowledge, the system can answer this question. So these 3 subtasks are detection, is this a knowledge thinking turn, selection, return a ranked top n best list. And the third one, generation, generates the system response. Here are some highlights of our approach. We mainly adapt the pre-trained models like Robot UniMM and GPT-2 to all the tasks. We also develop different ensemble algorithms for each task. Another subtask we want to highlight is entity tracking. The entity tracking aims to find all the entities mentioned in the dialogue. This is based on the observation that for all the knowledge here is actually organized with entities, and each entity will have multiple question answer pairs. So this entity tracking component is a replacement of the knowledge retrieval. Another key component of our approach is data augmentation. Typically, we use multi-root 2.1 for detection and knowledge ranking. And we also use the schema-guided dialogues, topical chat, and topic chat ASR for the entity tracking components. Okay, let's have a detailed look at our approach. For a better understanding of our approach, we will have some annotations in the following slides. The UI stands for the user utterance at turn I, and S for the system utterance at turn I. And for each knowledge key, is actually a tuple of entity E, question Q, answer A. And we also have some special tokens to mark some start of some context. For example, the user with the angle brackets means that this is a start of a user utterance. Similarly, we have our other special tokens here. For example, ENT with angle brackets means that this is a start of an entity or a domain name. Okay, so the detection task is a classification task. The context is just the dialogue history, and the target side is true false, or true is that this is a knowledge thinking term, false it's not. And the models we use are Robota, some variation of the Robota, and the UNIM. But this model only look at the dialogue history, so it will be difficult to generalize well to the unseen side because the dialogue history may not shown in our training side. So let's focus us on propose another model, which is a similarity-based model, which also takes into account the question-answer pairs. For example, the sentence 1 is the dialogue history, and the sentence 2 is a batch mode of the question-answer pairs plus a fourth dimension. This fourth dimension means that it's not a knowledge-seeking term. And the target side is the one hard vector. Then our model can minimize the cross entropy loss between the true distribution and the prediction. Okay, for the data augmentation, we mainly take the multi-root 2.1 and knowledge side as inputs. We simulate our training data in the following steps. As we know exactly offside of each entity in the dialogue of the multi-root 2.1, so it's very simple to replace these entities with an entity in our knowledge set. Then, if most of the slots in a dialogue are ready, then we can insert a knowledge-seeking term by using the questions in the knowledge base. We also rewrite these questions with an offline paraphraser here. In this way, we can simulate a lot of training data for the detection task. Our ensemble for the detection task is an error fixing ensemble, which aims to fix the false output of the baseline model. If, for example, if we take the joint model as our base model, then if the following two conditions are met, we will change the false to truth. The first one is the average score of the true score of all other systems is larger than a threshold. And the other one is that the last user utterance must match a regex rule. Those regex rules are collected from the validation set and the training set based on the error analysis we have. So let's move to the selection task. For the selection task, as we mentioned before, there are two subtasks. One is entity tracking, find the entities mentioned in the dialogue. And the other one is not ranking, just rank the knowledge of the given entities. So the first part is the replacement of the knowledge retrieval, because entity is much smaller than the number of the question answer pairs. So for the entity tracking, the data representation is very simple. The context is dialogue history plus the entity name. The target just predict the truth, whether this entity is mentioned in the dialogue. If this true score is less than a threshold, then this entity is mentioned in the dialogue. The models we use here is a robotic model. As we have a lot of annotated data, for example, SGD data, topic chat, and topic chat ASR. So we simply use this data as more training data. For example, we take the hotel name, slot, restaurant name, and even location in SGD data as the new entity tracking data. So for the knowledge ranking part, we have two kinds of models. The first one is point-wise model, which ranks each question answer pairs independently. Then we predict whether this knowledge is mentioned or is the correct one given this context. The other one is a list-wise model, which takes into account the batch size of the top 5 question answer pairs. Those top 5 question answer pairs are returned from the point-wise model, and the target side is just one hard vector. Then we minimize the cross-entropy loss again to learn the list-wise model. The base model we have for this task is robot wide and deep. That's from etc. 2020 last year. Here is some example of the wide and deep model. The deep part is for robot, and the wide part is some sparse feature we have. Here we only include 2 sparse feature here. The first one is the current knowledge a domain level knowledge or not. The second one is the current entity the last entity in the dialogue. For this task, we also apply important samplings for negative samples. For example, we do it in the following way. It's a k-fold cross-validated style, which means that we split the training set into k4. Then we train k models with holding each of the site as a validation site. Then we train k models and decode each validation site with the corresponding model. Then we can pick the difficult examples based on the scores, which is negative, but the score is also very high. So another thing we do is data augmentation. This part is the same as the detection task. And our ensemble for the knowledge ranking is very simple. It's just some probability of all the single systems. Okay, for the generation task, we have 2 kinds of data representations for the knowledge generation. The first one is we concatenate top 5 knowledges into the context, then let the system to pick which knowledge it should focus on. Then you can generate the response with this knowledge. And the other one, we feed each knowledge to the system and let the system to decide whether this knowledge is the correct one. If it is the correct one, then predict the response. If not, just predict false, then stop. The models we use are UniMM from Microsoft, GPT-2 and Dialog GPT-2. And we also have pre-tuned GPT-2, which is pre-tuned on a lot of dialogue data. We hope this model can generalize well on the unseen domain. Another question in generation is there is a discrepancy between the training and decoding following Zhang Yu 2019, because there is a discrepancy in the input of the target site. Because we train our generations models on the ground truth. But in the decoding time, this part is from the system output. So we we adapt their algorithms like word level sampling and sentence level sampling to our UNIM. Then we can do the following things. In the training time, we just decode the input sentence. We will get some outputs of the system outputs. Then we sample this with a decay sample probability, then move them to the target side of the input. In this way, we can simulate the decoding in the training time. So there will be no discrepancy between the training and decoding. So another thing for the ensemble for our generation task is a consensus decoding, which combines the MBR decoding and the MERT training. It's a linear model. Here it shows the linear model, which picks the minimum risk hypothesis from all n-best lists of all single systems. Here, S is a set of a single response for each single system. Phi is a function that measures the similarity between S prime and S. W is the weight. In our experiments, the function we use in total about 17 features. Most of them are relative metrics, for example, blue, mature, and several of them are system type. Means that this system UNIM or this system is GP2. Okay, let's move to the experiments. In terms of data, we have about 219K simulated examples for detection and knowledge ranking. And for the entity tracking, we have about 930K new data from SGD, TC, and TC ASR. For the validation set, we move portion of the validation set to the training set in order to increase the coverage of our modeling. So we have smaller validations in our development. Here are the results of our detection results on the original validation set, the full validation set. It shows that the data augmentation, DA means data augmentation, improves the F1 score on the validation set. But we can say that on the validation side, all the systems scores are very high and very close to each other. So we can move to the test site to give us a better picture. So here are the results on the test site. It clearly shows that data augmentation improved the F1 score. And our joint model generalized very well on the unseen set. And our ensemble further improve the score a little bit. So for the selection task, for the entity tracking, here we measure the measure with the recall on the validation set. It shows that data augmentation improves the recall on the validation set, and the average number of entities for each instance on the validation side is less than 2. So it's pretty good for us to focus on the second part of knowledge ranking. So as we mentioned before, the first knowledge entity tracking is mainly give us the recall at top 5, for example. It's pretty high on the validation set. For the knowledge ranking part, this is all the results on the validation set. It shows that the important sampling and data augmentation both helps to improve the performance. For example, important sampling is about 3 points better than the baseline system. And the data augmentation improves the score further. So we also tried the list-wise model, but list-wise ranking hurts the recall at 1. We didn't have enough time to investigate why this model hurts the performance. But in order to increase the diversity of all the single system, we just keep it here. Our ensemble improved the best score only a little bit on the validation set. So here are the results on the test set. It shows the same trend here, and our ensemble system improved the scores by 0.7 over the baseline system. Okay, let's move on to the generation task. So there are several experiments for the generation. The first one is because there is a discrepancy in pipeline framework, which means that we train our generation system on ground truth. But in the decoding time, we have decode on the system output. So we follow the same thing for the important sampling. We did tenfold cross-validated style with the selection system, which means that we also divide the training set into 10 folds and train 10 selection models and decode each subset with corresponding selection model. So the average recall at 1 on our training set is about 92. And this approach improves the BRU4 by half points, so which is significant. Another experiment is about the discrepancy between training and decoding. So we apply the word level sampling and the sentence level sampling on the UNIM large system. And the results shows that word level sampling improves the BRU4 by 1 point. And this one is also runs faster than the sentence level sampling. So we just use the word level sampling for all experiments. Okay, here are the results of all our 9 single systems on the validation set ranked by the BRU4, and also ensemble results on the validation set. So here we can see that UNIM large with word sampling and all knowledge works best on the validation set. And we didn't see clear conclusion about how the pre-tuned model works better or not. For example, for GPT-2 here, GPT-2 with pre-tune with each knowledge presented in the data representation works better than GPT-2E here. But we have another system called GPT-2E, GPT-2A, and GPT-2 pre-tune A. That system is lower than 13, so we didn't use that system. So there is no clear evidence that pre-tune on large data set or pre-tune on large dialog data set improve the performance. So our ensemble system can, with 17 features, can improve the BRU4 significantly on the validation set. It's about almost 2%. And on the test set, we see that our ensemble system only improved the BRU4 by 0.8%. So for better understanding why this happens, so we break down our scores into in-domain and out-domain dataset. Here shows the results, and it clearly shows that for the in-domain part, our ensemble can improve the BRU4 by 1.3%, which is pretty good. But for the unsynthesized, it's another round of story. And all the single system here performs very low than the in-domain data. And the gap between the best system and the other system is very, very large. So that's the reason why our ensemble on the unsynthesized doesn't yield better results. So that shows the reason why the overall improvement is less than 1 point. Okay, that's we rank first in the objective evaluations. and second on the human evaluations. So let's conclude our talk. So we think that ensemble for each task help to improve all the performance, especially the consensus decoding for the generation task. Another finding is that data augmentation helps the detection and the selection task. We also think that the joint detection and the selection learning approach generalize well on the unseen set. Another fact we found is that online sampling training for generation helps to improve the automatic scores. Okay, that's all for our talk. Thank you.
Okay, thanks Haitao for great talk and huge effort to do the so many different evaluations. Okay, so let's take a couple of questions. So is there any question or comment to Haitao?
Can I?
Sure.
Sure.
Okay, so GPT-2 didn't work well, right? So
yeah,
normally, you know, a long video description type of sentence can be generated very well, you know, fine tuning using a GPT-2. So did you check the similarity of distribution between your, you know, task and the GPT-2 model? So if the, you know, statistics or vocabulary coverage, or, you know, those are fundamental features are different, totally different. So it is very difficult to get the gain using a GPT-2 or bot. So
yeah. Our hypothesis is that the training objective for the GPT-2 and the UniM are quite different. UniM is designed for this condition or given the source predict the target, but for the GPT-2 it's just left to right decoder. It will also try to minimize the cross entropy on the source side. We didn't do the mask on the source side. So if we do the mask on the source side, I don't know the result it will be.
okay, so most of people believe that the, you know, bot or GPT-2 or 3, you know, fine tuning on top of the, you know, small task. The domain's different. Maybe it's difficult to get the gain, but in general, we would like to get the gain using those big model. So I really want to know the reason why you cannot get the gain from the GPT-2. Yeah. So hope in the future you can test the, you know, source side masking, or, you know.
Yeah.
Let's see. Yeah.
Because we have 9 single system here, we tried different kind of combination, but that's the results. I'm not sure that all other teams have the similar results if they have UniMM or BART, because that one is in the same trend, because they typically design for the generation.
Okay, thank you very much.
Okay.
Any other question or comment? I have a question. So in your data augmentation, I remember that for knowledge selection, you have tried to augment the data from different data sources, different external data sources. So I'm wondering whether you have done any ablation study to see which data was the most helpful to improve the performances.
For the entity tracking, we have this kind of experiments plus SGD, TC, and ASR data, because this part is on the original validation side. So
I see. So not for the test data set.
Yeah, because we are not allowed to.
Okay.
We don't know the exactly how it
I think
helps.
it would be interesting to see the effect on the test data set, especially in your data set for the augmentation, you use the ASR version of the topical chat, and I think that will be interesting to see whether how much that will affect to the performances for the spoken data that we have in the test data set.
Yeah, sure. Yes, that will be interesting because this is the in-domain data.
Okay. Any other question or comment? Okay, cool. Thanks, Haitao.
Thank you.
Okay, let's move to the second paper. The second paper is learning to select external knowledge with multi-scale negative sampling. And Siqi is here to present.
Yeah,
Okay.
yeah, I'm here. Yeah. Okay. Can you see my screen?
Yes.
Okay, great. Actually, we are team 19, and I'm Siqi. Today, I will introduce our work submitted to track 1, learning to select external knowledge with multi-scale negative sampling. This is the outline of today's presentation. First of all, we will introduce the task in brief, and then we will talk about the techniques that we use in our submission on a task-oriented conversation with unstructured knowledge exercise, including the schema-guided knowledge decision, the negatives enhanced knowledge selection, and knowledge-grounded response generation. Then we will introduce our experimental results, followed by the conclusion part. We all know that task-oriented dialogue systems have become very common in our daily lives, such as the personal assistants, the Apple Siri, and Amazon Alexa. Some systems can also provide customer services like restaurant booking. These systems usually rely on the predefined domain APIs to provide service. If we ask some queries beyond the coverage of these APIs, this system might not be able to answer it. It seems that they become less intelligent. Here is one example in this scenario. The customer asks, she wants to find a Chinese restaurant for dinner today. Based on the predefined API function, we can return the Peking restaurant towards here since this information is already included in our predefined API function and database. Well, if the customer continues to ask whether the restaurant provides high chairs for babies, this kind of detailed information is not contained in the predefined database. In this case, the system cannot answer it. However, this information is usually existed in a website, such as a review, the customer reviews, the frequently asked questions, and so on. In track 1, the system will leverage external unstructured knowledge for this out-of-API coverage queries. There are 3 steps in the task-oriented conversation with unstructured knowledge exercise. First of all, the system needs to determine whether to use the API function or the external knowledge given the current dialogue context. In this example, if the customer wants to find a restaurant, we can use information from the API function and return the restaurant towards her. However, if she wants to know some more information, like the high chairs for babies in this restaurant, in this case, we need to use the external knowledge. So if the knowledge-seeking turn detection is true, it means that the system needs to use the external knowledge. The next move is to select the appropriate knowledge with regarding to the context. In this case, the system selected one knowledge from this external knowledge database. Here is one knowledge snippet about the Peking restaurant, and the information is about the high chairs in the Peking restaurant. So with this selected knowledge, we can move on to the third step. So we will use this retrieval knowledge to generate one response towards our user. Well, to enhance the utilization of external knowledge and boost the quality of response generation, we have explored several advanced techniques. The first one is the schema-guided knowledge decision. Well, in the first task, for the knowledge-seeking detection, the most straightforward way is to rely on the dialogue context. However, this approach typically captures the frequent keywords or semantic patterns in a context. For some unseen conversations, this approach might suffer from some biased decision or poor performance. For example, in the training site, when the customer asks about the ticket fee of one museum in the Cambridge, so we may use the predefined API to produce a response, since the information of ticket fee is already included in the database of this city. However, if the conversation happens in another city, we may need to consult the external knowledge to generate this response. Even with the same context of ticket fee, the decision is different and different conversations. In practice, the system is supposed to know the functions of API and external knowledge before it makes a choice between them. So for the sake of comprehensive decision, we take both the dialogue context and the API and knowledge functions into consideration. While it is challenging to encode the structured API into the decision-making process, inspired by the recent progress in schema description, we employ the natural language descriptions to represent the functions of APIs. Here are some examples from the multi-words 2.2. For each service, it has a corresponding description. Here, the service hotel, the description is hotel reservations and the vacation stays. The supported slots and intents are listed under each service. With these schema descriptions, we can encode the structured API into the decision-making process. During the training process, the model learns to select the correct information type for the given dialogue context. Here, CT refers to the dialogue context. XI can be one schema description or one knowledge snippet. L is a label referring to use one kind of information. Here, for the conversational terms that rely on API services, the positive samples, XI, will be collected with the corresponding slot of the intent descriptions, and the negative samples will be collected from other descriptions or knowledge snippets. For the conversational terms that require the external knowledge access, its positive samples will come from the corresponding knowledge snippets, and the negative samples include other snippets and schema descriptions. So after training, during the inference process, if this condition is met, it means that the maximum probability to use one knowledge snippet is larger. So the system will consult the external knowledge for response generation. Otherwise, so the maximum probability might be one schema description. In this case, we will keep relying on the API services for response generation. Once determined to use this external knowledge, we need to select the appropriate knowledge snippet. Usually, the knowledge selection is trained to separate the positive samples from those randomly selected negative samples. While given the space of negative samples is extremely large, random sampling might lead to some coarse-grained class separation, and this is insufficient for the fine-grained knowledge selection. So as such, in this work, we introduce these multi-scale negative samples to improve the quality of knowledge selection. The negative samples are collected from 4 scales to increase the training difficulty. The first scale is random. It is the easiest one. So one negative sample will be randomly selected from the whole knowledge set. And the second scale is in domain. One negative sample will be randomly selected from those within the same domain as our positive sample. Here, if our positive sample is belongs to the domain of hotel, then we will select one snippet from the same hotel, same hotel domain. The third scale is in entity, so we will select one negative sample randomly from those belonging to the same entity as a positive sample. So for one positive sample as the entity of Peking restaurant, we will select another snippet as the negative sample belonging to Peking restaurant. And the fourth scale is cross entity. So one negative sample will be randomly selected from those belonging to the aforementioned entities in the dialogue context. Here, the aforementioned entity, let's take an example. Here, a customer and our system, they may discuss about Hotel A and Hotel B in a context. Then the customer may ask some more questions about Hotel A. In this case, Hotel B is the aforementioned entity in the dialogue. So the total ratio of positive to negative training samples is 1:4. Here, we can see that the training difficulty increases along with the refinement of negative sample scales. And we do observe the consistent improvement in the knowledge selection accuracy when we include the multi-scale negative samples. And during inference, the optimal knowledge snippet can be selected as follows. So just one with the highest selection probability. With the selected knowledge snippet, we can continue to the task of response generation. There are two basic requirements for the knowledge-grounded response generation. Firstly, the generated response needs to be coherent with the dialogue context, keeping a smooth conversation flow. Secondly, the response needs to express the information accurately without deviating from this original knowledge snippet. In this paper, we leverage powerful pre-trained models for knowledge-grounded response generation. The backbone of this pre-trained network is transformer block, and the input to the network is the sum of these four embeddings. Token embedding is a conventional embedding. We use segment embedding to differentiate the input information type, such as the knowledge snippets, dialogue context, and the response. The role embeddings are employed to distinguish the utterances from different characters, such as the user and the system. The relative position embeddings are also employed in the input representation. Well, as for the self-attention in the transformer block, the bidirectional attention is enabled to for the better understanding of the knowledge and context. The unidirectional attention is used for the autoregressive response generation. The objective of our training is to minimize the negative log likelihood loss. Here, T refers to the knowledge snippet. During training, we will use a golden knowledge for response generation, and during inference, we will use the retrieval knowledge for the response generation. And in the experiments, the evaluation of track 1 covers 3 tasks. The first task is the knowledge-seeking turn detection, and the second task is knowledge selection. The third task is the knowledge-grounded response generation. In the experiments, we leverage large-scale pre-training models of Plato 2 to boost the performance of 3 tasks. Plato 2 is a dialogue pre-training model. It is pre-trained with 694 million training samples extracted from Reddit, and there are 1.6 billion network parameters in it. And the experimental results on the test site is summarized in this table. During this computation, each team is able to submit at most 5 entries, and the method that we use are described as follows. In entry 0, we use a simple knowledge-seeking turn detection based on the dialogue context. In comparison, we use a proposed schema-guided knowledge decision for our task 1. And in fact, entry 1 is a full version of our proposed approach without any modeling sample. In the second task, we use a multi-scale negative enhanced knowledge selection. And in task 3, we leverage the pre-trained models for response generation. In entry 2 to 4, we carried out the modeling sample for the first 2 tasks based on using the pre-trained models of Plato 2, the BERT and Albert. And we explored beam search decoding with different beam sizes for the generation task. In the last entry, we tried to return the selected knowledge snippet as a reply directly. In this case, we can ensure the information accuracy, but for this response, it might be not coherent with the conversation flow. And from this result, we can see that entry 2 obtains the best performance among our 5 submissions. And the comparison between entry 0 and entry 1 shows that the schema-guided knowledge decision has obtained better generalization on these unseen conversations. And the obvious gap between the baseline and the proposed methods indicate that the strategy of multi-scale negative knowledge selection help improve this selection quality. As for the generation, the beam search with beam size of 5 obtains the best result. Well, besides this objective evaluation, human evaluation has been carried out for the final ranking. 2 metrics are employed in the evaluation, the appropriateness and accuracy. The appropriateness measures how well the system response is naturally connected to the conversation, and the accuracy assesses how accurate the system's response is given the reference knowledge. The evaluation score ranges from 1 to 5, the higher the better, and our approach obtains the first place in the final ranking. And we also selected several good and bad examples for the further analysis of our approach. Here are 2 cherry-picked examples. In the left case, the customer wants to find one hotel in the financial district of San Francisco, and he wants to know whether the staff can speak French or not. In this case, it shows that the model, our system, is able to select the appropriate knowledge and generate the high quality response. In this case, the accurate answer towards the user's query is not included in the surface contents of this knowledge. He asked about whether the staff can speak French, as the knowledge says languages spoken are English, Spanish, and Chinese. While our model still generates an accurate reply, the hotel doesn't speak French. It demonstrates the ability of natural language inference to some extent. And here are 2 examples with issues. The issues mainly come from 2 aspects. First, in the left case, we can see that a model fails to select the most appropriate knowledge due to the deficiency on training samples of some patterns. The customer asks whether the cache tape is included in the text feed. Actually, there are few samples about the cache tape in the training set. Secondly, for those complicated knowledge snippets with multiple segments, sometimes the system leaves a minor part and fails to generate the complete information. Now, these issues might be alleviated with a more advanced retrieval or generation algorithm in the near future. Now we come to the conclusion part. In this track, we have explored several techniques to bolster the quality of task-oriented conversation with unstructured knowledge access. We introduced the schema-guided knowledge decision for better generalization on unseen conversations. And we include the multi-scale negatives to improve the knowledge selection accuracy. And we also leverage the powerful pre-trained models for high quality response generation. Our approach was ranked as the first in the final human evaluation. Our pre-trained models and source code will be released at GitHub. Currently, we are in the final stage of release review. Hopefully, these models will be made publicly available in these 2 days before the end of our workshop. Yeah, that's all. Thank you.
Thanks, Siqi, for the great talk and many interesting ideas. So is there any question to Siqi? I have a quick question about your knowledge selection module. So I understood that you have some negative sampling for training your model. So I'm wondering how did you select the candidates in the inference time for your knowledge selection? So did you do any filtering based on the entity or domains, just like you did for the negative sampling?
We will use all the candidates and perform ranking for all the candidates. So so efficiency might be a major problem of the current approach. Yeah, since I need to go through all the candidates and input the context and each candidate into the network. We noticed that some reviewers suggest give us some suggestion that we can rank the candidates using the hierarchical structure of the database. For example, first the domain, then the entity, and then the candidate knowledge snippets. I think this is a really good suggestion. And recently, we also tried some other strategies to accelerate it. So we use some dual encoders. So we will encode the context into an embedding, and we will encode the each knowledge snippet into one embedding. And then we will use some KNN search algorithms to retrieve these knowledge snippets. So with this way, we can accelerate it. Yeah, we hope that more results can be released in the near future. Yeah.
That's great, thanks. Any other question or comment? Yeah, so there was a question in the chat from Vinny. The very interesting presentation, thank you. What is the typical inference time from the model?
Oh yeah, I think this is similar to the last question. Yeah, the time. Currently, the inference time is a major issue for the approach. And so for this generation task, the average time to generate one response is 1 second per sample. Yeah, even just for the third stage. And so we think with some the acceleration strategy of this knowledge selection and the average time for this whole process must still be 1 time something. Yeah, one second something. Yeah.
Did it answer to your question, Vinny? Okay. Okay, great. Any other question or comment? So I have another follow-up question, so related to the efficiency of the model. So this is not only for your system, but also for baseline and other top systems. So I think the ensemble was very effective in improving the performances of the tasks that we had in this challenge track. But I'm wondering, so I'd like to learn from your opinion whether that is realistic in the system in practice.
For the model example,
so I think this is okay for this kind of offline evaluation. But if we want to have this kind of system in production, so I think the efficiency and some memory restriction, all these steps need to be considered. So I'm wondering, so what do you think about the, whether this is realistic to have this kind of ensemble in the practical system or not?
Well, personally, I think it might be difficult to carry out the online modeling sampling in the practical deployment. Yeah, so maybe maybe we will here we give some results of the single model without any modeling sample, and we can see we have some percentage drop here, or we have 4% drop in the knowledge selection part, but this is a trade-off between efficiency and accuracy. Yeah. So for the practical deployment, I think we may choose the single model. Yeah.
Okay. Yeah. Thanks. So any other question or comment for Siqi? Okay, great. Thank you.
Yeah. Thank you.
Okay. Let's move forward the last paper in the session for track 1. The final paper is titled the RADGE, Relevance Learning and Generation Evaluating Method for Task-Oriented Conversational System. And today, Liang is presenting. Liang, we don't hear you, so you are muted.
Okay, can you see my screen?
Yes, and
okay,
we hear you.
Hi everyone. We are team 10. It's my honor to be here to join the DSTC9 workshop. I'm going to introduce our systems for track 1. So my presentation will include 3 parts. First part is introduction of the track 1. And second part is our proposed method. And third part is the final result and the future work. So the object of track 1 is developing the end-to-end dialogue system to understand the relevant domain knowledge and generally system response with the select knowledge. It has 3 tasks. The first task, knowledge select thinking turn detect. By give the dialogue contents, the system need to decide whether the AAAI API is sufficient to answer the user's question. If not, it must be turned to the knowledge selection database. And second task, knowledge selection. Once a given dialogue is created as a knowledge thinking turn by the task 1, the system should select which knowledge snippet is most appropriate to answer the question. And the third task, the knowledge graph generation. The model need to generate a response with the knowledge snippet and the dialogue contents. And there is a data set we are used. We have a C domain and un-C domain in the evaluation phase. And we have dialogue contents and knowledge snippet and ground truth response. So in the evaluation method, we are using, in the first task, we are using precision record and F1. And in the task 2, we follow numbers of standard IR metrics as an evaluation, including the cost of top 1 and top 5, and MR5. Sorry. in the third task, the knowledge ground generation. Oh, sorry. In the third task, the model was evaluated use the Bru and RADGE and meter and the human evaluate. So that's our proposals methods for the track 1. About task 1, the knowledge thinking turn detection. We may pay attention in UNC domain because F1 of the baseline method in the UNC domain is 22 less than the C domain. In order to improve the performance of the model in the UNC domain, we use the relevance learning to predict the connection between the domain API and the contents dialogue to decide whether the dialogue is the knowledge thinking turn. So the electorate has a good performance in a general UE task compared to other pre-training model with the same parameter size. So we use the electorate pre-trained model. The input of the model is domain name and the API keyword and dialog contents as the input. And the loss function is the binary clause entropy loss. We have 2 sub-loss, domain and the API keyword loss. About the API keyword, we have 2 kinds of the API keyword. DB API keyword and knowledge API keyword. DB API keyword is extracted from the DB JSON file. And the knowledge API keyword is extracted from the each domain knowledge. We got a top frequency word in the domain knowledge and scale a common word. Then we will get our knowledge API keyword. There is an example of our DB API keyword for all the hotel and the knowledge and the DB API keyword for the hotel. So the DB API keyword for the hotel include postcode and address, phone number, parking, and knowledge API keyword of the hotel include Wi-Fi, breakfast, and bed, smoking, pet cleaning. There is the training sample construction of our models. For each dialogue contents, there is knowledge thinking. We construct a positive sample with the correct domain name and the DB API keyword. For each dialogue, there is knowledge thinking. Construct a native sample with other domain name and the correct DB API keyword. And for each dialogue, there is knowledge thinking. Construct a native simple with correct domain name and the knowledge API keyword. And for each dialogue, there is knowledge thinking. We construct a native sample with the correct domain name and the DB API keyword. When we use this model, the F1 is 4.1% better than the baseline with the electric. And in the word of the prediction, we compare each dialogue content with 5 sets of the DB API keyword and 1 set of the knowledge API keyword, which is from ANSI domain. And let's mean we create 6 prediction sample for every dialogue. For a dialogue, the predict of 1 sample constructed with C domain DB API keyword is knowledge thinking turn. This dialogue is the knowledge thinking turn. If the model predicts the ANSI domain sample which constructed with knowledge API keywords is greater than the DB API keywords, the dialogue is knowledge thinking turn 2. Otherwise, it's not a knowledge thinking turn. When we use this method, the result of F1 is 8.4% better than not use. And in the task 2, the knowledge selection, we also use the electric pre-training model. And the input model is the dialogue contents, entity name, and domain name, and knowledge snippet. And we use the binary clause entropy loss. When we use the electric large, the recourse of top 1 is 6.7% better than the baseline. And we have 3 optimized methods about this task. The first, we have entity recognition model to predict entity of the dialogue contents. So in the evaluation phase, we do not predict all the knowledge snippet in the knowledge database. We only construct the candidate sample with the knowledge snippet in the entity candidate. So the recourse of top 1 is 13.5% better than the standard baseline with the electric. And also the speed of the predict is faster than the predict all the knowledge database. And the second optimized that we use in the multiple task training and top up entity domain and knowledge loss in our total loss function. With the multiple task training, the model can select the knowledge based on the domain and entity and knowledge information. And third optimized, we using the official native sample to replace the random method. We train a standard model first and predict a training data set with this model and got a top 3 easy confused knowledge snippet as the native samples. And when we use the multiple task training and the official native sample optimized, the recall of top 1 is 8.9% up. In the task 3, the knowledge ground generation. In this part, in the task 3, we do not modify the generation model. We propose a generation evaluate method to alternate evaluate the results of the generation model. The generation evaluate model using the electric pre-training model the input of the model is dialogue contents, knowledge snip, and response. And the loss function is the binary cross entropy loss. First, we train 3 GTP small model and generate the response for the training data set, and construct a positive symbol with each group of dialogue contents and knowledge snippet and a group and a ground truth, and construct 3 negative symbol with 3 response generated by the GTP small model. When we use this model to select the best result from the Tang generation model as the final result, the blue is 1.3% better than before, and meter is 2.2 better than before, and RADGE is 1.4 better than before. And about the final result and the future work. The table reports the human evaluated result for the track 1. The third one is our result. We got 0.5 better than the baseline in the average. And about the future work, we will improve our performance of our systems. And thank you for your attention. I'm looking forward to exchange the follow-up questions.
Okay, thanks, Liang. Any question or comment for Liang from audience? Okay, I have a question. So you mentioned that you have focused on the unseen domain. So how to handle the unseen domain for the knowledge-skeleton detection. And you proposed extracting some keyword from the database and APIs. And you incorporated that into your model. So my question is, what if the domain and entity in the new domain is not available in your training your model and in using your system? So
Okay.
right now, so our test data set includes some unseen knowledge and unseen domain, but that is still, a kind of the subset of the multiverse data set. So because the unseen domain in our test data set is the attraction, and attraction was still in the original multiverse data set. So if you use the database file from the original multiverse, I think that will work well for the test data that we have. But what if we have totally new domain, so which is not available in the training data? So do you think your method can be generalized to this case as well?
For the unseen domain, in the C domain, our method is also the C domain. The performance in the C domain is better than the unseen domain. Also, when use these methods. So, but we have improvements in the unseen domain. In the illustration, we split our data set in the two parts. In the training data set, we are remove the hotel domain in our training set to evaluate our models.
Oh, I see. So you did some overlation study based on the existing domain in the training data set. So removing domain.
Yes, removing hotel domain. And so we can evaluate our methods in a testing data set. We are split testing data set into two parts. One is the C domain, and the other is unC domain is the hotel. Because we already remove our hotel domain information in our training data set. So we evaluate our methods in this way when we do this check. But in our final model, we use all the data to training these models.
Okay, sounds good. Thanks. Any other question or comment for Liang? Okay, so if there's no question or comment, so I think that's it for the track 1 oral session. Thanks, Liang, for presenting and answering the question. And thanks again for all the attendees to this track session and also all the presenters in this session. And we will have a poster session for the other papers, the other participating teams in DSTC9 track 1 later today. So I encourage everyone to join the poster session to discuss some more details for other systems as well. So, thanks, everyone.